Hey everyone. So the last part of our equilibrium chapter is looking at a couple of industrial processes that involve equilibrium. The first of which is the Haber or Haber-Bosch process, as it's also known. So the Haber process is used to create ammonia. So it takes nitrogen and hydrogen and forms it together to make ammonia. Again, you can see a chart here of just where some places where ammonia is used. So fertilizers are 85% of the ammonia usage that's produced. Textiles, explosives make up 5%, and others, which includes things like plastics, so making polyamides from ammonia. So poly, like we learned in the organic unit, meaning many pieces. Um, So this Haber process is one of the most important chemical processes that's been developed. Okay, so it's so important. It consumes more than 1% of humanity's energy production. Now that's huge. So imagine of all the cars, of all the computers running, of all the different power processes and plants producing things, this process, this making synthetic ammonia, is 1% of our entire energy production of the world goes into this process. Okay, this ammonia that's made is responsible for feeding 1/3 of the population of the world. Okay, so it goes into these fertilizers that are made through the Haber process. And on average, half the nitrogen that's found in a human body actually comes from the nitrogen formed in the Haber-Bosch process at some point. Okay, so let's take a look at how a little bit of how the process works. So it is an equilibrium. Something quick to note before we do that is equilibrium in industry is very interesting because we want to be getting the product formed as much as we can. Yet the more product we form, the more as the concentration goes up, according to Le Chatelier's principle, the more that it's going to move back to the reactant side. So trying to figure out and fine tune these reactions is very important to the chemical industry. So to make ammonia, okay, we take nitrogen from the air. Our air is composed largely of nitrogen. And we take hydrogen from natural gas, so sources like methane. Okay, we mix them together in the proper stoichiometric ratio, so 1:3. Okay, and we mix them and react them to make ammonia. So they react. Okay, these are the conditions. We're going to talk a little bit more about the conditions later on. And remember, when they react, it's in equilibrium, so both reactants and products are going to be present. So how do we then just take out the ammonia? How can we remove the nitrogen and hydrogen? Well, we do that by cooling them down. So when we cool it, ammonia turns to a liquid, and the nitrogen and hydrogen, so ammonia is extracted as a liquid, and the other gases, nitrogen and hydrogen, go back and get recycled back into the reaction. Okay, so why ammonia? Let's take a look at the boiling points of how this works, or the condensation point, you may call it. So ammonia has a boiling point of negative 33 degrees Celsius. So if we can cool it to there, we can liquefy ammonia. And nitrogen is negative 196 and hydrogen is negative 253 Celsius. So by just cooling it down a little bit, so even a minus 40, we can condense all of the ammonia out of the reaction and have the nitrogen and hydrogen continue through as gases. Now, why is ammonia's boiling point so drastically different? Remember, one of the key things is it has hydrogen bonding because it has those nitrogen-hydrogen bonds. So that hydrogen bonding is what leads it to be such a higher boiling point, those much stronger bonds. Okay, so let's take a look at the conditions required and study this reaction from an equilibrium perspective. So how can we affect concentration, pressure, temperature, and what is the use of a catalyst? How can we change these things in order to maximize our production of ammonia? Okay, so first off, the concentration. Obviously, we're going to continuously add nitrogen and hydrogen into our system in order to produce ammonia. So that pushes it to the right-hand side, the equilibrium. What we also do is we remove ammonia as it's formed. Okay, so as ammonia is formed, we decrease the concentration of ammonia. Remember what that's going to do is push the equilibrium to the right to make more ammonia, trying to overcome that stress from the removal of it. So it shifts to the right, or the product side is the effect on equilibrium. For pressure, we have 1 and 3, so we have 4 moles of gas on the left and only 2 moles of gas on the right. So pressure, again, all of this is according to Le Chatelier's principle learned in the previous section. Okay, so pressure, if we increase it, we'll move to the side with the least number of moles. So we're going to want to use a high pressure. Okay, and that'll, again, shift equilibrium to the right. Temperature, if we take a look, we have an exothermic reaction. Okay, so that is the same. When we have an exothermic reaction, that means heat is being produced. So we can actually treat heat like a product and add it directly to the product side. So treat it just like you would a chemical. So it's here on the product side. If we want to shift the reaction to the right, we're going to need to decrease the heat. So due to the fact it's exothermic, decreasing the heat, lower or having a low temperature, will shift to the right or to the product side. Lastly, we have our catalyst. So the Haber process uses an iron catalyst. Okay, iron, it's very cheap. It's a heterogeneous catalyst, so easily filtered out of reaction if need be. And a catalyst, remember, a catalyst does not have any effect on the position of equilibrium, but what it does do is allow the equilibrium to be reached faster. So example, if we start it with all nitrogen and hydrogen, right, it would allow us to more quickly produce the ammonia and reach the equilibrium point, but it doesn't actually shift the equilibrium once it's established. Okay, so these are our conditions. Now there's a key thing here though. If you remember back to our kinetics unit, we have to use a low temperature, but remember about the rate of reaction. The lower the temperature is, the slower the reaction is going to occur. So equilibrium doesn't tell us anything about the rate of reaction. It only tells us about how much product or how much reactant we have. So we want to shift it to the right, but we have to look and we have to consider the fact that the lower the temperature goes, the longer it will actually take to reach that equilibrium. So we have to find a balance. So what conditions will the Haber process actually use? So taking a look at this graph, on the left-hand side we have our yield of ammonia, okay, at equilibrium, so our percentage that we get out, and our pressure on the x-axis, pressure in atmospheres, and these lines each represent the production of ammonia at different temperatures. So you can see, obviously, the lowest temperature that we have on this graph, 350 Celsius, we produce the highest percentage of ammonia. 550, the rate is going to be much faster, but we're producing much lower yields. It's also more expensive to heat something up. Okay, to higher temperatures means you need stronger metal equipment to withstand the heat. You need more energy to actually create the heat. So the higher the temperature, the more costly it's going to be. And also with pressure too, the higher the pressure, the more costly this is going to be. So we need to find this balance. And the balance they found to get the most efficient yield of ammonia is a temperature of 450. Okay, so we're looking along this whatever color bluish green line here. A pressure of 200 to 250 atmospheres. Okay, and with this, they find that the yield of ammonia production is around 20%. Okay, so this is considered a moderate temperature. It's not extremely high, and this is a pretty high pressure though, 200 to 250 atmospheres. But any higher pressure leads to significantly higher costs and also leads to risks of explosions, okay, and other dangers. And higher temperatures would lead to a lower yield. Lower temperatures would lead to the reaction taking forever to actually take place. So these conditions are the most ideal conditions that we can get, so to find that balance. Okay, so this is the Haber process or Haber-Bosch process. The next process we're going to look at is the contact process. So the contact process is used for producing sulfuric acid, which again has a lot of industrial purposes, which we'll look at next. The first step in the production is taking pure sulfur from pure sulfur, reacting it or combusting it using oxygen to make sulfur dioxide. We then add more oxygen to the sulfur dioxide to make sulfur trioxide. And then lastly, that sulfur trioxide is combined with water, which produces sulfuric acid. So it's this middle step, this equilibrium step, that we're interested in, because this is the one that we have to affect the equilibrium to maximize our production of the sulfuric acid. Okay, so again, we have to look at that balance. So let's take a look at how the Le Chatelier's principle affects sulfuric acid. Affects this equilibrium in the contact process. So first off, here's some, to the left here, you can see some uses of sulfuric acid. So again, fertilizers, ammonium sulfate, detergents, so different cleaning agents. It's used in a lot of paint. It's used for making fibers, rayons, and paper, so different polymers and plastics. And it's also used, if 30% goes to other uses, including explosives, pesticides, dyes. So sulfuric acid has a huge range of uses, which is why it's so important to produce in industry. So let's take a look at our properties again and see how we can change them to maximize production of sulfuric acid, sulfur trioxide in this step. So first of all, same as the Haber process, we would remove sulfur trioxide as it's formed, pushing it to the right. Pressure, we would use a high pressure because we have 3 moles of gas on the reactant side and 2 on the products. So that would shift it to the right. Temperature, once again, we have an exothermic reaction. Our change in enthalpy here is negative, so we want a low temperature. Shifting it to the right, and the catalyst in this case is vanadium 5 oxide. And the catalyst has no effect on the equilibrium, but once again is used to speed up the rate of reaching the equilibrium. Okay, so we have the same situation here as we did with ammonia, where we have a low temperature is giving us the best yield, but also a slow rate. So we have to again find a compromise here. So for the contact process, the actual values that are used is we have a temperature of 450. Okay, so same as the Haber process, so a moderate temperature to keep the rate up, but not too high to shift the products to the left. And we use a pressure of 2, it's actually 1 to 2 atmospheres, and a yield of, and that produces a yield of 99.5%. Okay, so you might ask, well, why don't we use a pressure of, use a pressure of 100? That'll make a yield even more. But there's not much of a point because, again, increasing the pressure can lead to dangers such as explosions. It is incredibly expensive to do. This is already producing 99.5% yield. So there's not really any reason. We're almost getting 100%. So there's not very much of a reason to increase the pressure anymore beyond that 2 atmospheres. Okay, so this, in summary, we looked at the Haber process and the contact process and how Le Chatelier's principle applies to both and their conditions and compromises that we had to make to maximize our production of equilibrium reactions in industry. And this brings us to the end of the equilibrium chapter.